Hello, welcome back student to the design and analysis of algorithm subject. As we are in the unit 3, so today we are going to see the traversal technique. Before going to that, we will see what we have done in the previous lecture. In the previous lecture, we used the dynamic programming method, and in the dynamic programming method, we completed the multi-stage graph. Completed the multi-stage graph. What is this? In the every stage it is going to take the decision which route is the best route. Okay, so when you see the previous video, then you will going to know what is the multi-stage graph. So today we are going to see the traversal technique. The traversal technique, we have the graph. This traversal technique we are going to perform on the graph. Okay, and what is graph? Graph is a cycle. Okay, and graph has a vertices and edges. Okay, and DFS, this is the short form. DFS, depth first search. Whatever in the graph, which one is in the depth, the lowest, not we cannot say the lowest, but in the depth of the graph it will go and get the value first. Okay, one more topic is there, that is BFS. BFS, that is breadth first search, but as per your syllabus only you have a DFS, so we are going to see only DFS. Okay, first we will see what is graph, then we will go with the DFS. So here this is traversal technique in the unit 3, graph traversal. What is the graph? Graph is a pictorial representation of a set of objects where some pairs of objects are connected by link. Okay, connected by link. See, this is, it is connected from A to B, it is connected from B to D, connected from D to C or C to D. You can say this is called undirected graph. Undirected graph means there is no we can say this is a two-way. You can go from A to B, okay, or you can go from B to A. That is undirected graph without any arrow. Whenever we have an arrow, there is a directed graph. The interconnected objects are represented by point term as vertices. This A, B, C, D, E is all called vertices, or you can say, okay, the both has the same, but in the graph you need to say vertices, and the link that connected the vertices are called edges. These two things are very important in the graph. First one is vertices, A, B, C, D, E. Edges means which is connected from A to B. Whatever the link is there, that called edges. We call edge. And what is this A, B? Is called vertice. Okay. Yes. So how will you make a formula? I hope you understand this because you have already completed the graph topic in second year. Okay. So in the data structure. So here just to show you the traversal. Okay. Formally, a graph is a pair of set, vertices and edge. Means whenever we have a graph, these two things will be there, vertices and edges, where V is a set of vertices and E is a set of edges. Connected the pairs of vertices, take a look at the following graph. Okay. So in the graph you can see A, B, C, D, E, the vertices, and from A to B and A to C and C to D and D to E. These are the edges. Okay. I hope you understand this graph topic. Okay, and how we can represent that as per the formula like this. How we need to write P is equals to how many vertices are there? A, C, E. 5 vertices. 1, 2, 3, 4, 5. Okay, 5 vertices we have. And how many edges? Edges is also 1, 2, 3, 4, 5. But we need to give the name from A to B, from A to C, from B to D, from C to D, from D to E. Okay, is the, so when we write here vertices and edges, then your graph traversal is this. Okay, now here computer science or information technology, graph traversal, also known as graph search, refer to the process of visiting, checking, and updating each vertices in a graph. Such traversal are classified by the order in which the vertices are visited. So this depth first search is what it will do. It is visiting the edges. Sorry, visiting the vertices. When it is visited from A to B, okay, then it is visited. So how the process is going on, how it is checking and updating or updating the vertices in a graph. Such kind of techniques are there in the graph is two: depth first search and breadth first search. But as per the syllabus, you don't have this, so just we will go with this. Okay, and depth first search will use the stack. The stack. What is the stack? What method it will follow a stack? Stack will follow last in, first out. LIFO, LIFO. Okay, last in, first out. Means whatever the vertices is going to insert the last, that will be take out first. Okay, that is called stack. Stack follow that. Okay, take the example like if we have a bunch of books. Okay, books one by one, one by one. Okay. So if you want to take a book, you cannot take the first, this last book. Cannot take this last book. First, you need to remove these things. Okay, then only you can take this. So, what does it mean? Whatever the item is going to insert, whatever the book you are going to keep on the top, the last one, that we will remove first. The last in, first out. So that is what we say. Whenever you are adding here, that is called push, and whenever you are taking out from the stack, that is pop. Okay, this terminology is whatever, whenever you are inserting the item, whatever you are doing any operation in the stack, that is pushing the data. Then whenever you are taking out from the stack, that popping, pop. Okay, fine. So here in the depth first search traversal algorithm, traverse a graph in a depth word motion and use a stack to remember to get the next vertex to start a search. When a dead end occur in any iteration, okay, so here it is starting from here, the first one, okay, that it is storing in the stack example, okay, storing in the stack. And here D A, from A to D is going, again D is adding here, from D to G is adding, and here from G to E, and it can be go to G to F. So I am doing G to E first. Then from E to B, E to B. Okay. Is there any connection between this B? B is connected to S, but already we have S here. Sorry, okay. We have S here, so we need to pop this. Okay. After popping this, again it come back to position E. There any connection here? Already G, already it is added. This also need to pop. Then after from G to F, there is a connection. Okay, there is a connection. Come back from here to here, then here to here. Again now from G to F. Now the graph will be like S, A, and F. Then from F is connected to C. This is I am showing the roughly. I have example in the down, the bottom, that we will take the example. This all process we will do in the step by step process to score good marks. Okay. So here after adding all the things, when we reach to the dead, so now we need to remove all the items from stack. Okay. This is a process we need to perform in the depth first search. First it will go to the depth. Okay. When it is starting from S, where it is stopping here, means here dead. So this one is a depth one of the graph. Then again, okay, like this we need to perform the operation. So let's take the example and we'll solve. Before going to solve that, there is some rules. Okay. Rule number 1, visit the adjacent unvertices vertex. Means whatever the adjacent vertices, you need to visit that, unvisited. Mark it as visited. Display it, push in the stack. What we have done here, whenever we reach from S to A, this is a adjacent vertex. Okay, you can go from anywhere, here, anywhere, but I am going from here. So S to A, when I am going, so here it is showing this one is a unvisited. This was not visited in the first time, so that item we need to add in the stack. Okay, the first rule is whatever the adjacent is unvisited, that should be visited and display in the stack. Next, rule number 2, if no adjacent vertices is found, okay, then pop up a vertex from the stack. It will pop up all the vertices from the stack which do not have adjacent vertices. Means whenever, like here, just now we reach here on the B, then from here there is no adjacent vertices which is unvisited. S is visited, so here it does not have any unvisited. At that time what we need to do, we need to do the pop operation. The pop operation is remove from the stack. If it is happen to all the vertices which is no adjacent, then we need to move from the stack. Okay, then rule 3, repeat rule 1 and rule 2 until the stack is empty. Okay, until the stack is empty, we use to perform the operation. Let's solve the problem. Step 1. What is step 1? I am taking this graph. This graph S A C, the vertices, is vertex S A B, and this is my stack. What is this? First, initialize the stack. And before going to start this, you must know why we are doing, because in this graph we need to find the cycle, okay, and we need to know all vertices, whatever is present in the graph, that is visited or not. That is the main advantage, means we'll going to know all the vertices are visited or not. Okay, so let's do. First we initialize the stack. The second one, I am here now, so I mark the S is visited and put into onto the stack. Now explore the adjacent vertex which are unvisited. Okay, so we have three nodes or three vertices. 1, 3. From S going to 3 vertices. We can pick any of them. One can select anyone. From this example, we'll take the node in an alphabetic order. Okay, you can take A, B, C, anything, but we will go with the alphabetic order. So what we need to take the next? We need to take the next is alphabetic order is first A. So I am going to the A now. A is a that from the A, how many adjacent vertices which are not visited? Only one. Only one unvisited adjacent is D. Already S and D we have. So S is already visited. This is unvisited. So this unvisited, you need to select unvisited node and you need to push in the stack. Okay, you need to push the stack. From the D, we have the 3 A and C, but A is already visited and B and C is unvisited. So how we can you can select any one of this. You can select C or you can select B, but we will go as per the alphabetic order. From B and C, first will come the B. So we will select B. We'll select B and add in the stack. Okay, when we add in the stack, now we have to check the unvisited vertices, adjacent vertices of B. Just check it out. S already visited, D already visited. Now when the both are visited and it does not have any unvisited adjacent node, so you need to pop the B from the stack. Pop this B from the stack. That means no unvisited adjacent to B. Okay. So when we remove the B, so what are the remaining? S, A and D. Okay. So where is our top is D. Where we are now? We are at the place of D. Now from the D, how many adjacent vertices are there? 3. A and C. But from this, which one is a unvisited? C is a unvisited. So select the C and push in the stack. Okay. C select the C and push in the stack. Now only unvisited adjacent node is from D is C. Okay, from D and C, D to C is unvisited. So we visited and push in the stack. Okay, now we completed the stack. Now what we need to do? There anything from the C is unvisited vertices are there from S and D? No. So what we need to do? We need to take out the C as a pop. Then after that we have a S, A, D. From this 3, our node is here. From D, is there any unvisited adjacent? No. So what we need to do? Pop. Okay. The next is we have S and A. From A, is there any unvisited? No. All are visited. So now is pop again. Then and the last we have only S. From the S, is there any unvisited adjacent node to S? No. So just take out the S, pop, and make it empty the stack empty. Okay, stack is empty. That means in this graph all are visited. Okay, so a C does not have any unvisited adjacent. So we need to keep popping the stack until we find a node that has unvisited adjacent node. Till that we need to remove the unvisited adjacent node. In this case, there now we are keeping popping until the stack is empty. So we did the stack is empty. That means the graph has a cycle and is a connected graph. A connected graph. What we say? Connected graph. Okay. So this is about the EFS, the algorithm. What is the algorithm? Whatever we are doing in the top, the example, the same thing you need to write here. First DFS, vertices, and even undirected graph. What the graph has, as I told you, two things: vertices and edges. Okay, n vertices and array visited initially set. N vertices and an array visited initially set to 0. First, we are in setting the 0. Okay, no one is dead. That means stack is empty. This algorithm visited all vertices table from P. Okay, graph and visited are globally. Then we visited. Then we are popping. So visited V is equals to 1. Whenever the visited, if like S is visited, it's as a for each vertex W adjacent from P to. If anything like W means unvisited, if visited W is equals to 0, then FS W to follow all the operation. All the operation. Okay. This is about the depth first search of graph. Okay. The next class we are going to see the bi-connected graph, bi-connected component, and all the topics from the traversal technique. What are the articular point? Okay. So what we have done today? So traversal technique, we saw the graph and we completed the depth first search example as well as the algorithm. Okay, thank you very much. We'll see you in the next class.